a collection of individual charged particles that are in some kind of uniform arrangement. And let's say I have another charge out here. Now, if I wish to find the force on this independent charge, let's call this one capital Q. And I say that all of these are just a small amount of charge broken up into lots of little pieces. Well, you can probably recognize that although there might be some symmetrical things here, truthfully, each one of these is going to have to take in, one at a time. Find out the force, the direction of that force, and then begin the process of doing a vector sum. Now, there might be ways to limit how individual it all is. Like perhaps I can say they all line up on this line, and I could find the perpendicular distance from where my one charge is to where one of the charges is over there. And then I might be able to recognize that, well, if this distance is d, then this distance is 2d and 3d. There might be some symmetries I can work on here that would help me perhaps find the size of this force, but in terms that have some repetition. Now, if you don't understand fully what I mean, consider if this distance were z. Now I'm just throwing some stuff out there. The charge that's here and the charge that's here would experience a force of q over z squared times k. And that would have to be the force between those two charges. Does that make sense so far? That one's not hard. The next one is going to offer us a little more resistance, meaning that we're going to have to probably be a little more thoughtful about this one. Not worrying about direction yet, just worrying about the size of that force. I think you could probably agree that with just a little bit of foresight, I could figure out what that force would be. Right? I would need to know the distance or the length of the blue line, and I could use the Pythagorean theorem to do so. Does that make sense? Still following? Because I can start to see that there's going to be some repetition, right? This next line, I don't have to think very much about it. It's going to be Are you seeing where I'm going with this? And there's some symmetry, right? Meaning this one would be the same, just on the other side. And this one would be the same, just on the other side. If it was symmetrical on both sides, I could probably come up with a way of finding out the size of this force by adding up each of these individual little forces. Now, there'd be more to do. I don't want to minimize this too much. There's more to do. This is a tough problem because even if it's perfectly symmetrical, even if there are the same number of particles on each side, which would make it nice, wouldn't it? If there was that kind of symmetry, I would know then that the net force would probably be just this way. Because for every contribution of the force that's in this direction, there'd be an equal and opposite contribution of the force in that direction. So I could probably start working this problem the same way I did the two-charge problem yesterday. You guys all doing okay so far? Not a huge deal? But you understand, algebraically, this is a lot of work, isn't it? If I start putting these together, I'm looking at denominators that are going to get bigger and bigger, and I don't see any easy way I can add up all those denominators together. I think this is going to have a very complex-looking solution. There might be some commonalities, like all of them are going to have this in the numerator. And when I start working out the angle part, I'm going to have some commonalities that all the cosines are probably going to have similar features. They'll have a z over r, just like yesterday, but every one of those r's is going to be different. So you can see that this would probably produce a pretty complex problem. We have to study not this problem, though. We have to study this problem. Here, as we added up individual pieces, we would have a summation as our portion of our problem. A summation is a way of adding up individual pieces. In fact, if you remember how a summation works, I probably could structure this summation. Meaning, and I'm speaking to a subset of you now. Some of you know what I'm about to write, and some of you don't. And if you're one of those people who don't worry too much. You won't be doing many summations at all. And many of you don't know summation notation. I mean, let's get a feel for this. Who does know summation notation? So apparently I've got 5 people in the room who know summation notation. So a summation usually indicates, has a counter involved and talks about which is the first of something you will sum and for how many you're going to sum. Let's say there's 8 particles on each side.
Professor Shaw, I don't know if this is intentional. Were you going to change the screen back?
No.
Okay.
I want to stay right here for a minute.
Okay.
I could write this as a summation. I could say the top is always Q, Q, K, and the bottom is always z squared plus I times d quantity squared. This is what a summation would look like. This says the size of my force is equivalent to this function, which is Coulomb's law, and I am going to add up each one of these forces, starting with I equals 0 and adding up each of the charges. Now, if there's 8 on the left side and 8 on the right side, I might need to multiply this by 2 to indicate that there's 2 sides. Now, there's some stuff I'm making that is wrong, that wouldn't work. But I'm just giving you a taste of what a summation would look like. It would find the part of the problem that's repetitive and help us structure a way of adding them together. Now, with a summation like this, if you've done any summation work, you know that you can find recursive equations that can represent a summation. This is something that used to be taught, and I don't think it's being taught any longer. How many of you have had to do that? Come up with a recursive equation that would do the summation for you? It's probably a mu alpha theta thing, I would assume. Is it in Algebra 2 or Pre-Calc anymore?
Pre-Calc, yeah.
You guys did a little bit of recursive equations? We're not going to do anything like that because this problem isn't going to be presented to us. What if it's not a bunch of just individual charges? What if this is like a piece of metal that has now had a charge placed upon it? Maybe this whole piece of metal, which is length L, has charge Q. Something that's not a point charge, but an amount of charge distributed in some kind of uniform fashion. And let's say that I have another charge that's located right at the midpoint of the bar, but offset a distance z away. I think you would all agree that, well, if capital Q is positive and this little point charge is positive, there would be a force this way, away from that bar. Right? There'd be an electrostatic repulsion because I have a charge that's positive acting on another charge that's positive. But you understand that by spreading out this charge, I am probably changing the nature of how big that force is. Would you all agree with that statement? So how do you deal with a problem like this? Yes? We would be doing some summing, right? What we did over here, but this problem will be presented to us. You see, in this problem, we don't have individual pieces of charge. We have a uniform structure of charge. But we still have to treat it like we're doing a sum. Like we're going to be adding up the contribution from each piece of charge. We're going to take this bar, which is length L and charge Q, and we're going to break it up into individual pieces. And then we're going to add it all up using the integral function as a means for doing so. Now, integral function is the wrong way to say that. The integral process as a means of doing the sum. Now, I want to caution you. Some of you are barely holding on, and I know that. That doesn't change the fact that this is a curricular topic we have to talk about. This particular problem that I'm going to show you, this exact one that's right here in front of us, would never be asked on the test because of the actual math involved to finish it. But this problem is a great place to start when it comes to setting up what one of these sums looks like. The problems you will be offered all have mathematics that you will be successful in doing. Generally, integrals that are polynomial in nature or relatively simple. We are not going to do the last step of any of these for weeks, which is to actually execute the integral. All we're going to do is set up the integral, which is something that's not taught in calculus, but is taught in here. So I want to talk to you about how we set up the summation, the integral, for a problem like this. It's going to take a bunch of steps, and I'm going to try and, I would love to say we will finish this today. We will not. So it's one of those things where a single problem might take us 25 minutes to get set up. And that's me being optimistic, all right? So it'll take patience, and you'll need to be paying attention to where we are in the problem. But does everybody at least understand the setup? I have a point charge, and it's being acted on by the entire length of this bar. Is everybody okay with that? Now, to understand that, it is important that we maybe come to grips with some symbology that will be helpful here. So I'm going to come back to this picture, but charge per unit length is. This object has a charge density equal to Q over L. That is the charge density of the piece. I was given the entire charge. I was given the entire length. So I can write that as a charge density. I want you to be aware you can be given lambda separately and just be told to work your problem in terms of lambda, or you can be given expressions to use to figure out lambda. Both are reasonable things that happen on the AP exam, and you need to be prepared for either one. So step one for any of these kinds of problems will be to create your charge density. Be aware of how you would deal with the charge density. And whether it's a linear problem or a problem that uses a sheet of charge, something like a disk that's charged up or something like that would work, or whether you'd have to use volumetric charge, like a ball or a cylinder or something. These are all reasonable things that could happen on our exam. So we need to be prepared for any of them. In creating a charge density, you're putting something that has an amount of charge over a shape. So we're going to focus on linear density today and for the next couple of days. And then we'll add areal density, and then we probably won't do volumetric density for weeks. Just to clean this up, I'm going to move the Q and the L out of the way. Step two, after I have found something I'm going to use to represent the charge density, I need to identify a single piece of my object. Doesn't matter where it is. The goal with identifying this piece is to build up a vocabulary of ways of describing all of the pieces in the bar. I'm going to create the vocabulary to do so. So step 2 is just identify a portion of your object. I'm putting those pieces here to kind of create size, that I'm talking about a small slice of the object. Doesn't matter where on the object you decide to find your piece. What you're going to try and do here is build up a vocabulary that describes where each piece of the object is. And this is tough, but this piece we know has a small amount of charge, dq. And by definition, that small amount of charge is equal to lambda times dx, where dx represents the length of the piece. Now, for math purists, it doesn't have to be x, right? I can use any symbol to represent length that I want. And you should generally use symbols that make sense. By using x, I'm suggesting that the green line lies along an x-axis because it's linear. But I could use any letter I want here. Does everybody understand that? Now, in order for us to make an identification here, I want you to be reminded that we're using Coulomb's law. So once I've identified a piece that I'm going to be using for Coulomb's law, this is going to be treated as if it's a point charge. I want to treat it just like a point charge and build up what I feel is an appropriate way of writing out Coulomb's law for the interaction between these 2 points. Now that's a very complicated way of saying I'm going to draw a line from here to here. I'm going to call that line R. And I'm going to say that the force on charge Q is going to be equal to charge Q times the piece of charge times K all over R squared. I haven't even started to think about direction or anything. I'm just trying to build Coulomb's law around this piece of charge. Okay, we all good so far? Now, of course, every piece of charge is going to have a different R. You guys noticed that, right? So the next thing you want to try and do is see if there's a way to define your values in this function in terms of things that you could easily identify in the problem. Now, hear me out. My charge is located a distance z away from the middle of this bar, which means this distance is half of the bar, and this distance is the other half of the bar. You guys follow so far? That makes sense to you, what I'm doing? Well, if this is dx, then I would probably be correct in stating that dx is located a distance x from the center of the bar. Since I've chosen dx to represent the length, I could use a pointer to point out how far away dx is from the center of the bar. Now, the job of what I'm doing now is to see if I can find an easy way to point to each one of the charged pieces of the bar. So here's what I want you to think about. Can I use X as a means of pointing at each piece of charge in the bar? Could I do so? Like, is there an X that would represent every piece of charge along the length of the bar? Could I use an X to identify this piece of charge? Sure, just be a bigger X, wouldn't it? And I could use an X to determine this piece of charge. It would just be in a negative direction, right? If this is the middle and it's 0, then half the bar lies on one side and the other half lies on the other side. And it's pretty clear to me that X is going to be a number between L over 2 and negative L over 2. Right, that would get me from one end of the bar to the other. In fact, what I'm doing here is defining the geometry that will describe every single piece on the bar. I need something that will do that. Now, there are other ways I could have chosen to do this. I'm using linear values because I think it's easiest, but there's other things we could do, and we'll see other ways of doing this in the future. Also, this tells me that I could identify where this piece is by using triangle trig. If you don't understand what I mean by that, I could rewrite this as Q dq k over not r squared, but z squared plus x squared. What I'm trying to do is find a way to find the size of the force from every piece of the bar in terms of variables that I could use to define one part of the bar and every piece in between till I get to the other part of the bar. I couldn't use R to do that before, but I can use X to do that because X has reasonably defined limits. X has to go from negative L over 2 to positive L over 2. Are we okay so far? I know this isn't easy, and eventually you'll be having to do this on your own. But you're seeing it for the first time, so I'm going to move forwards, but I know Owen had a question, so it seems like a reasonable time for me to stop and let some of your brains, catch up. All right, so just going back a little ways, oops, not all the way. Going back a little ways, added the cosine, because I know that all of my actual components of force are going to be perpendicular to the bar. I interpreted the cosine in terms of the variables that are in my problem, because I'm trying to turn it all into as few variables as possible, and eventually recognized that I could sub in variables that I've already defined. Now, I want to stop for just a minute and talk a little bit about this transition here and what we're actually doing, because it might not be obvious, okay? For every theta, there's a different r, and for every r, a different theta, right? As I move along the bar, r is getting bigger and the angle's also changing. By translating r into z and x, I move from a bunch of different r's to a bunch of different x's. That doesn't change very much. I still have a x changing with every single piece of the bar. But what I'm eventually trying to do is get just one variable that I have to worry about changing for the whole problem. I'm trying to get rid of r, theta, and convert them all to something that has to do with x. That's what I'm doing here. So each one of these substitutions is to get to the value that is represented in the piece of the bar dx. Because I know x is going to go from negative L over 2 to positive L over 2. I have a very clear delineated start and end to where x begins and where x ends. So I'm trying to get everything in terms of x. Does that make sense so far? Are we sure? I see your head shaking, but if you have a question, you should ask it. I knew Owen would.
Just quickly, so where?
All right, so your question, yes, I'm not just adding cosine. What I'm really saying is that each piece of the force that I want to look at, I only have to look at the part that is the cosine, the adjacent portion of that force. Yes.
So the cosine was always in Coulomb's law, because if you have the linear ones, it's just equals 1. Right? So your angle is 0.
No, I don't want you to think of it that way.
Okay.
Let me, just a brief aside, okay? And I'm just drawing this because I want a clean space for just a minute, because I might have, in my zeal to move forwards, not been clear about something. Does that look like it's the middle or close to the middle? It'll do. Every piece of this bar has a different force on this charge. Right? That's from that piece. And that's from that piece. I'm just picking two. Okay? Every different piece of the bar is going to have a different size force acting, and a force that's in a different direction. Everybody okay so far? This is where you guys who were doing this just a second ago should really pay attention. If I look at this perpendicular line, I know that this force is going to have a component on the other side that's the same because there's symmetry here. Right? There's a piece of charge over here that's going to provide a symmetrical force in that direction. Everybody okay with that? This is where we had the 2-point charges yesterday. So I'm going to add up all of these forces. But I only need the forces that are along this perpendicular line. So what I'm really, I guess, saying is I don't want to add up all the forces. That's not what I want to do. I want to add up just the components along the line. When I tacked the cosine on, it was because I was changing the parameters of the sum, and I didn't make that clear. So I'm going to see if you know things, okay? This was on your, kind of on your practice test. Imagine I have a string, just a piece of string. And let's say that piece of string is 2 meters long. And I put it on a scale, and the whole thing measures 550 grams. So it's thick string. Okay? Then take a pair of scissors, and I cut it up into various lengths. All right? One of those lengths is 25 centimeters. What would be the mass of that 25 centimeter length? You should be able to do this. You shouldn't need my help. Now I'm going to assume that you guys went about this probably one of two ways, but probably the most likely way was you guys set up a proportion. How many of you set up a proportion to do this problem? Okay. Now, I'm not going to walk around and see who could and couldn't do this problem. But I do think that enough of you could say, well, 550 is to 2 as my unknown mass is to 0.25. Some of you recognize that 0.25 was 1/8 of 2 and maybe just figured it was 1/8 of the total mass. That's still a proportion. Regardless of how you interpret the proportion, it's still a proportion. Like you could have said 0.25 is to 2 as x is to 550. Similar, I mean, it's the same proportion. You understand that? I mean, cross multiply, you're still going to get your answer. One of the reasons I would prefer you think of it like this is because what this term represents. This term represents the linear density of the string. the mass per unit length, linear density. Density is a term you know, and you probably learned volumetric density when you were in chemistry. You learn that different materials have physical properties, and those physical properties, one of them is density. What you probably didn't recognize is that there's density for all kinds of things. And so in your pretest, if you'll recall, I talked about mass densities, 3 different kinds of mass densities. This is one. Guitar strings are sold by linear density. If you go buy a pack of guitar strings, you're probably not buying them based on that, but that's how they are created. Same with every stringed instrument. The heavier strings play the lower notes, the lighter strings play the higher notes. It's inertia. If I want to play a higher note, I need it to move faster, so I get myself a lighter string. Fair enough? It's linear density. If you go buy rope or wire, you're still buying it based on density. So any type of measurement can be made to be thought of as density when it comes to its size. So you can have mass density, you can have charge density. There's all sorts of types of density out there. We focus on charge density in this class, but I was hoping that maybe like the guitar string example would at least be something you could recognize. Same with like thickness of paper. You get nice paper, it feels thicker, doesn't it? Cardstock feels even thicker, but all of it is super, super thin. It's sold based on its areal density, the density per unit area. Paper is sold like that. There's a measure that they use for paper. It doesn't matter, it won't come up here. But you would assume that thicker paper would be more mass per unit area. Does that make sense? And you're aware of volumetric density, which is what you were taught in chemistry, mass per unit volume. We're going to focus on mass per unit length for the time being. Not because of mass being the particular thing here, but because one thing that we could have done is we could have called, or I could have given you, not the mass of the string and the length of the string, I could have given you the density of the string. I could have told you what the string's density was in terms of grams per meter. If I gave you this, what's known as the linear density, this is the symbol that we use for linear density. It is the Greek letter, lowercase lambda, L, so linear density. In this example with the guitar string, it would be grams per meter. When I use a linear density, if I want the mass of a piece, mass is going to equal lambda times the length of the piece. This is how you use a density. Everybody following along so far? Any questions about this? Okay, so let's see if you can extend this. I could write this as a piece of the mass equals lambda times a piece of the length. How are we doing now? Symbology still okay? No trouble with the symbology? Okay. Now, here's where you'll need to make a small jump. If the piece is very small, calculus would ask that we don't write it with a delta, but we write it with a d instead of a delta. So the last step would be to say a piece of the mass, dm, equals lambda times a piece of the length, dx. Still means the same thing. If I want to know how much mass I have, I just multiply the density times the length. This is still the same thing. However, it has a bit of a mathematical distinction in that dx here is a very small piece. And in fact, you'll learn in your calculus class, or you already have, that we consider it to be infinitesimally small for uses in mathematical functions related to calculus. It's still no different than a delta. It's still a piece. Everybody okay?